Good morning. Welcome back to the video lecture series, Probability Theory and Stochastic Process. This is Dr. P SREENIVASULU. Today we are going to discuss about the Gaussian random process. Already we have seen random process concept for a single random process and multiple random process, mean value and autocorrelation function, cross correlation function, covariance function. All these things we discussed previous classes. Now, the Gaussian random process means we are going to, already we know a Gaussian random variable. So the random variable concept, again, we are going to be discuss, or we are going to apply that Gaussian random variable concept in random process also. So always this is going to be expressed in whatever it is, probability density function. Now here we are going to be consider x of t. The x of t is a random process. In this x of t, there is a n number of random variables. That n number of random variables, if you see here, at time t equal to 1, time t equal to 2, time t equal to 3, and so on, time t equal to n. So that entire random process is going to be like discretized. x1 is equal to x of t1, comma, x of t2. X of t2 means what? At time t equal to 2, whatever the value we are going to be get, that is going to be x2. That is another random variable. So at time t equal to n, we are going to get whatever the information that is going to be right xn. So these are all a random process. From the random process, we are going to be get random variables. Already we know how to write a Gaussian density function for random variables. So that is going to be right in terms of times here. Now at time t equal to t1, t2, and so on, tn, we are going to be discussed here. That is the only thing. Previously, random variables, these are not function of time. Here, there is a function of time. That is the only difference you need to remember here. Whenever the density function, more than one variable, more than one random variable, it is a joint density function. Suppose it is a single random variable, we are going to call it as a probability density function. Whenever there is a two random variables, we are going to call it as a joint density function. Here we are considering from the random process n number of random variables. So it is going to be called jointly probability density function. Now here the random variables are jointly Gaussian for any n value. For any n value, and at any time instance, t1, t2, and so on. Then the random process x of t is called Gaussian random process. You see the statement. When we are going to call it as a Gaussian random process means the random variables jointly Gaussian for any n value. That means n equal to 1, 2, 3, and so on, n. And then we can see at that corresponding time instance, the random process of x of t is called Gaussian random process. Now you can write this jointly Gaussian density function. Already we know from the concept of random variables. Simply here, the only difference is here we are going to be write function of time. Previously there is fx of x1 comma x2 comma and so on xn, and corresponding here for x1 related to t1, x2 is related to t2. At a different time instance from the random process, whatever the waveform we have, from that random process, we are going to be like discretization of that random process. We are going to consider different time instance. Now, the standard Gaussian density function formula is equal to exponential of -1/2 x minus x bar. X means that corresponding event. X bar is mean value of that random process here. And Cxx means covariance. Cx is inverse. X minus again x bar. So we need to consider first of all x minus x bar into covariance, inverse covariance, and then again x minus x bar divided by root of 2 pi whole power n magnitude of Cxx covariance matrix. So it is the standard Gaussian function, Gaussian density function format. That is where just interpreted in random process. The same concept is already available in random variable also, multiple random variable concept. Now where we know what is the x bar? What is the x bar? Expected value of x generally for random variable. Now here it is a random process. So we need to write x bar indicates expected value of x of t. Expected value of x of t. Suppose it is a time t equal to t1, x of t1, a time t equal to t2, x of t2, a time t equal to t3, x of t3. So that is the meaning. And then covariance matrix. And already we have seen this covariance, how to define this covariance, Cij is nothing but Cx1, x2. Meaning this Ij indicates it is a n number of variables. We need to consider any two, whether it is x1, x2, x2, x3, x1, x3. For that combinations, we are writing it is a Cij is equal to, we know the concept of covariance, how we can write. It is the expected value of generally x minus x bar. And if suppose there is a two, the covariance means we are going to consider two instants, x1 minus x1 minus x1 bar into x2 minus x2 bar. Now here, this x1 minus x1 minus x1 bar, x2 minus x2 bar, suppose there is a two instants, but here there is a n number of instants. So that's why we are keeping here a subscription is I. So xi minus xi bar, xj minus xj bar. So this I is again integer, j is an again integer. So that is, you don't confuse here why it is I, because there is this concept is we are discussing for n number of random variables. That's why we are going to write this ij. Okay. Now then you can write this if you distribute this expected value, whatever it is, this concept already we know, this covariance concept. So it is equal to Cik is equal to Cxx of T1 comma Ti comma Tk. The whatever the same formula we are going to write in terms of Ti Tk. So it is equal to Cxx of T1 comma T2. Already it is from covariance property. It is autocorrelation minus individual, means it is a mean value of this one. It is a mean value of another time instant. Whatever it is suppose it may be 1, 2, 3, or it may be 1, 2, 3, like that. Okay. It is about a Gaussian random process. Now coming for this Poisson random process. So Poisson means there is a, suppose the previously also we discussed about this Poisson's density function. During this a particular time interval, how many number of the number of number of cars arriving at the park during from 0 to 9 to 10 or 12 to 1, like that. The counting purpose we are going to use this Poisson random process. Again you see here the Poisson random process x of t is a discrete random process which represents the number of times, you listen this point, number of times some event has occurred as a function of time. As a function of time. That's why I said during the time, suppose 9 to 10 at the car parking station or at the toll plaza. So how many number of cars are arrived within that interval? So it is a discrete case and it is represented number of times some event has occurred is a function of time. So it is a integer value. So non-decreasing sample function. Now we see we can clearly get, this is that word, a single event occurs a random time. A single event occurs random time. Counting the number of occurrences with the time is a Poisson random process. If it is a random variable, it is not related with the time. Suppose it is a random process, it is related with time. Now, if you observe this graph, it is going to be increases based on time. At time t1, it is like this. Time t2 increases, while coming for this Poisson's counting process. Now it is right in the uh, formula basis for this. The number of occurrences of an event in any finite interval of time. It is described by Poisson's distribution. And then if you get Poisson distribution, we'll get the density function also. So probability distribution function, probability of x of t is equal to k. This is lambda t power k into e power minus lambda t divided by k factorial. Now corresponding density function, we are going to write this k equal to 0 to infinity, lambda t whole power k, e power minus lambda t divided by k factorial delta of x minus k. So it is the formula. Suppose there is any problems on Poisson's, we are going to write this formula. So simply we will give the data corresponding time interval and what is the time interval, how many number of times that event occurred, and what is the overall probability density function. We are going to see in the problems. Now, you see a problem is on a jointly wide sense stationary, a problem, jointly wide sense stationary. He has given y1 of t is equal to x1 cos omega t plus x2 sin omega t. And y2 of t is equal to x1 sin omega t plus x2 cos omega t. If we observe this one, the terms are uh, interchanged. Here, first one there is a cos, and there is second one is there is a sin. And in the second case, first one is a sin, and second one is cos. Now, the question is where x1 and x2 are 0 mean. Means what? Expected value of x1, expected value of x2 are 0 mean. And independent random variables. Independent means whenever if you calculate expected value of x1, x2, it is equal to 0. With unity variance, the random process y1 of t and y2 of t are individually wide sense stationary, but not jointly. So if we calculate autocorrelation between y1 of t and autocorrelation between y2 of t, these are independent of time. Whenever we calculate cross correlation between these two, jointly and means cross correlation, it is not wide sense stationary. It means it is a function of time. So first of all, you whatever the question is going to be analyzed properly. So whether the two random process are wide sense stationary individually means you need to calculate mean and you need to calculate autocorrelation. And autocorrelation is independent of time. And the mean value is a constant, then we can say it is a wide sense stationary process. Now the conditions as given here. So the condition of random process x of t to be a wide sense stationary. First one is mean value is constant. Autocorrelation point is independent of time. You know what is the mean value? Expected value of. He has given the random variables x1 and x2 are 0 mean. So he has given the clue. Expected value of x1 is equal to expected value of x2 is equal to 0. Expected value of x1 is equal to expected value of x2 is equal to 0. Next, sigma x1 square is equal to sigma x square is equal to 1. Sigma x square is equal to sigma x2. Here the sigma x1 square is equal to sigma x2 square is equal to 1. So what is the sigma x1 square? What is the sigma x2 square? It is a variance. Variance he has given it is a 1. Now it is the given data. From this given data, you need to calculate mean value. So the mean value is expected value of y1 of t. So expected value of y1 of t. What is the y1 of t? You can write x1 cos omega t plus x2 sin omega t. And you observe the given whatever the concept. Now it is if we apply this concept for individual times, because these are independent, expected value of x1, expected value of cos omega t plus expected value of x2 and sin omega t. We know this expected value of x1 he has given it is a 0 mean. Expected value of x2 It is the German. So no need to calculate this expected value of cos omega t, expected value of sin omega t. Even if we calculate the expected value of cos omega t, expected value of sin omega t, it is also 0. The average value of cos, the average value of sin is always 0. Next, similarly, if we calculate expected value of y2 of t, anyway, the terms also same, but there can be interchange. So this term is also going to be get 0. It is about mean value, individual mean value. Now, if we calculate autocorrelation between y1 and y1, means for y1 of t, if we calculate autocorrelation, formula, expected value of y1 of t into y1 of t plus 2. Now, what is the y1 of t? We know x1 cos omega t plus x2 sin omega t into x1 cos omega of t plus 2 plus x2 sin omega of t plus 2. Now, it is the expected value concept. Okay. Now, this expected value concept, you can multiply all these terms. If you multiply all these terms, x1 cos omega t with x1 cos omega t. Next, x1 cos omega t with x2 sin omega of t plus tau. Next, x2 sin omega t into x1 cos omega t plus tau. x2 sin omega t into this x2. If you multiply all these things and then multiply all these things, and then if you apply this expected concept, after multiplying, if you apply this expected concept, and if you observe this one, expected value of x1 square cos omega t into cos omega t plus tau, and x1 x2 cos omega t into sin omega t plus tau, plus x1 x2 sin omega t into cos omega of t plus tau, plus x2 square sin omega t into sin omega of t plus tau. And then if you see this expected value of x1 square is unity, as given. Expected value of x1 square is unity. No, as given. This is a expected value of x1 square is equal to unity. So that is going to be right. Sigma x1 square plus x bar whole square is equal to 1. Next, expected value of x2 square is also as given unity. But because of this x1 and x2 are independent, expected value of x1 and x2 is equal to 0. So if we substitute all these inputs, whatever the data is given, now in this equation, it is going to be 0, it is going to be 1, and it is 0, and it is going to be 0, and it is a 1. And then if you see this formula, cos omega t into cos omega t plus tau, sin omega t into sin t. So cos A, cos B plus sin A, sin B, you write cos A minus B. So omega t plus, if you write this one, these two cancel, omega t gets cancelled, omega tau. It is a function of tau, so independent of time. Similarly, if you do for second random process also, because the only terms are interchanged, that's why it is also going to be a function. Now coming for cross correlation, if you find a cross correlation between, this means y1 of t and y2 of t plus 2. y1 of t and y2 of t plus 2. And if you multiply these terms, and if you observe this anyway, this expected value of x1 square anyway, it's a constant. And then these are independent. These two terms are going to be 0. And remaining terms, if you observe, there is a cos omega t sin omega of t plus tau plus sin omega t cos omega of t plus tau. Now, if you see, it is a cos A sin B, sin A cos B. So it is not like a cos A cos B plus sin A sin B. It is a cos A sin B, sin A cos B. So it is a sin A plus B. What is the sin A here? Sin A is omega t plus what is the B? Omega tau plus omega t. Now if we observe this one, it is a function of time. It is a function of time. So whatever the given problem, it is a individually, means y1 of t one random process, y2 of t another random process. y1 of t individually is a wide sense stationary, y2 of t individually wide sense stationary. And if we see this y1 of t and y2 of t jointly, but it is not wide sense stationary. It is the conclusion. It is the problem, a small problem on this jointly wide sense stationary. So today I'm going to stop this class. We will see in the next class in another problem.